All right, Algebra 2. For 3-3, people ask for number 6. Basically, the idea is we have these three inequalities, and they're going to make some sort of, maybe it's a triangular region, perhaps it's a unbounded region, but there's some sort of region that is going to be identified as the solution region for these three inequalities. And we're going to try to find all the vertices, which is where the lines intersect. Um, right now, I'm thinking it might be unbounded, just because I'm looking at the slopes of these two lines here, and they look to be parallel to each other, which is a pretty good indicator that it's going to be an unbounded situation. Once we find these vertices, we're going to plug them into the function to see if there's a minimum or maximum. And what's interesting about this, when we're using an unbounded region, we're going to have to test some other points out there to see if we can get beyond the two values we get for these intersection points, um, just to see if there is which one is actually a true minimum and a true maximum, or um, if there is any. So let's go ahead and do a quick sketch of these three graphs. Just I like to number these things. That 6 is in the way there. So first inequality, second and third inequality. It just helps with my brain to kind of organize what I'm seeing up on the screen here. And for the most part, um, like these two intercepts here are pretty good. This one, not so nice. So it looks like I'm going to have to go at least by twos for the y-axis. So I'll go by twos for the x-axis as well. Uh, 1, 2, 3, 4, 5. So that's really a 10. 1, 2, 3, 4, 5. That's really a 10. 1, 2, 3, 4, 5. Negative 10. 1, 2, 3, 4, 5. That's a negative 20. I'm going all the way down there because I know I have a y-intercept of negative 18. Um, 1, 2, 3, 4, 5. There's 10. Okay. Now, because everything's doubled here, what makes it really nice is counting off the slopes for all of these things works the same. But we'll put some points in here to double check. So positive 6 as a y-intercept. This is equation 1. And it's going to go up 2 to the right 1. So it goes up 2 to the right 1, which would be this little point in here. And I'm actually going to go up 2 and to the right 1 again. And you can see, if you count the overall bigger triangle there, it's up 2 to the right 1. So that's going to work just fine. We're going to keep doing up 2 to the right 1. That only works right now because the scale is the same on both the x and the y-axis. If my scale was slightly different, like if the x-axis was going by ones and the y-axis was going by twos, that wouldn't necessarily be the case. Oh, that's a horrible line right there. Let me uh, let me do this something a little bit better here. That looks like right there, and we'll go there, and then we'll use this guy. Okay, that's a better looking line there, and that is equation 1 in red. I'll kind of put a little red circle here. I like to color code stuff. We'll do equation 2 in green. Oh wait, I forgot. This is a less than, so we want to shade everything below that line, and we'll get to shading that later. Uh, 2x minus 8, so I go to negative 8 here. And again, same thing, goes up to that point there. And so it's got the same slope, which is pretty nice because it tells me that we're going to have parallel lines. I think I mentioned that earlier. So there we got parallel lines. And this one is shaded above. So you can see right now the solution region is in between those two lines. And that's equation 2 in green. And we'll do the final equation here, or inequality, 3, negative 2x minus 18. So let's go to minus 18. And now this one here is going to be a negative slope, not quite perpendicular, so it's basically going to go down 2 to the right 1, down 2 to the right 1, or up 2 to the left 1, up 2 to the left 1, up 2 to the left 1. And that's nice right there because I see it crossed a nice neat spot here. And the other one I'm not so sure. I think that's the right spot there, and that should be enough for us to draw our line. Yep, that looks good. So this point here, where inequality 3 and inequality 1 cross, looks like it's pretty legible. That looks like 1, 2, 3, negative 6, comma, 1, 2, 3, negative 6. And I could plug that into both those inequalities real quick to check it and make sure it works. 2 times negative 6 plus 6, that's negative 12 plus 6, or negative 6. Okay, so that one worked. And negative 2 times negative 6 minus 18. So that's positive 12 minus 18 equals negative 6. So yeah, this point works for inequalities 1 and 2. I just checked it really quick with some algebra, right? Just the graph looked like it was close enough to read the point, and now all I have to do is check to see what this other point here is. Oh, sorry, I forgot to say why I care about those points. I forgot here. This is greater than. So you can see above the blue line, in between the green and the red line, is our solution region. I forgot to shade that in. That's a pretty important step there. This whole scenario. It's one of those things. This is the solution region. It's where all the solutions to the system of inequalities are. But when it comes to finding the minimum and maximum with the optimization function, it's all about the vertices. So I need to find that other point there. And I don't know exactly what it is. I could use something like GeoGebra or NumWorks to figure out exactly where those 2 points intersect. But I'm going to do systems of equations real quick here, because I see that I have equation 2, 2x minus 8, is equal to y, but y is also equal to negative 2x minus 18. When I add 2x to both sides, I get 4x. Add 8 to both sides, I get negative 10. So now I can see I get x equals negative 2.5. That's why I figured my guess wasn't going to be right. I must have remembered from doing this problem before, which is an advantage most people don't have. But basically the idea was it wasn't an easy point to read or to check, so I just defaulted to solving system of equations. Now that I have the negative 2.5, all I have to do is plug it into one of the equations. What about equation 2 there? 2 times negative 2.5 minus 8. That would be negative 5 minus 8, or negative 13, right? 2 times 2.5 is negative 5. Minus 8 is negative 13. Okay, yeah. So this point here should be negative 2.5, comma, negative 13. All right, so those are my two vertices. Now I need to check them in the function. And what I'm going to do to kind of save screen space here is this is work that should be saved here if I'm solving that one, but I'm going to kind of just shuffle it off to the side so I can keep everything here on the same screen. All right, so I've got my 2 points, and I'm checking it into the function f of xy, 5x minus 4y. So my first point I'm going to check is negative 6, 6. And I'm just going to write the result here on the side so that way it's a little bit easier. So I'm plugging it in. 5 times negative 6 minus 4 times positive 6. That's negative 30 minus 24. So that's minus 54. That'd be a good thing to double check in my calculator here. 5 times negative 6 minus 4 times 6. Yeah, negative 54. Perfect. Of course, I don't know if that's min or max yet. It could be either. I mean, you might guess min because it's a big negative, but who knows? Maybe the other one is going to be even more negative. Okay. Um, now, um, 5 times negative 2.5 minus 4 times negative 13. So this is, I get a feeling this is going to be positive, just because of that negative 4 times negative 13. That should be a pretty positive number. And yes, I get 39.5. Okay, so it looks so far like it has a minimum of negative 54 or in a maximum of 39.5. The problem is this is an unbounded region. Solutions go up forever to the up and to the right. So all I have to do is pick some point that's really far out there and test it and see if it kills whether the min and max here. Now, there's a couple ways you can do this to make it easier on yourself. You can choose points that are on the y-axis. That makes the x 0. It's easier to calculate. But it doesn't really matter as long as it's any point in the solution region. How about that one right there? What is that thing? That is positive 8, 14. Okay, so let's see what we got here. Positive 8, 14. So 5 times 8, that's going to be 40. 14 times 4, that's going to be, that's 56 or something like that. 5 times 8 minus 4 times 14. I get negative 16. Okay, so that one didn't really help me out. It doesn't really knock any of the two out. So now I'm going to pick another one. Let's try that. Go back to that point there that I said was good. How about 0, 1, 2, 3, 6. 0, 6. It's good to pick ones that are on the lines too, because those are usually the extremes of everything. So 0, 6. So 5 times 0 minus 4 times 6, that's negative 24. Still doesn't help me out. Let's try a point on the green line somewhere. Bump, bump, bump. How about this one up here? That's 12. 16. This might be kind of similar to the third one we tried. You're basically having to. Oh, it's behind my webcam here. Sorry. You're basically trying to figure out some sort of pattern and see if you can get anything to change. So here I get negative 4. So still nothing is really happening there. One of these points should knock it out though. Let me try this point here. That would be 8, 12, 14, 16, 18. 8, 18. Let's try that. 8, 18. I'm not even going to write that one down. I'm just going to start plugging stuff in right now. And that's a negative 32. 8, 18 is a negative 32. So it's seeming like those might be good maximums and minimums. Though usually one of them, if it's unbound, one of them comes out. Because, I mean, you could choose like infinitely large numbers here. So give me a second. I'm going to pull up my teacher's edition here and take a look at this problem. See what the book says. And this is what I'd be doing if it was odd and I feel like I wasn't getting something that I was expecting. I'd just be looking it up in the back. They say that there should be something different here, but I'm not getting it. So let me check to see what they say. See if I can figure out why it's happening that way. Sorry, this is turning into a longer video, but 3, number 6. So my graph looks good. So it says no minimum, max of 39.5. So I should be able to find a number that is more negative than 54. Well, what number could that be? That's more negative. Oh, how about if I try this point right here, the x-intercept? Remember I said the axes are nice? That's looks like it's 3, sorry, negative 3, 0. No, that's not going to be, that's just going to be negative 15. So negative 6, negative 6. What about a point down in here? What's that? Negative 4, 1, 2, 3, 4, negative 8. Oh my, oh my. You're going to laugh at me when I point out this. I'm going to highlight in green here so you can see it. This point of intersection we were talking about is negative 6, negative 6. But look at what I wrote into my equation here. Oh man, it almost makes me want to start the whole video over. But it's okay. Mistakes happen. That's a thing that happens in math. Um, yeah, this true value here should actually be negative 6. And when we do that, you can see that those three options all cancel that one as a minimum. So the minimum is gone. No minimum. The max is 39.5 at negative 2.5, negative 13. All because I missed one little negative sign in there. Maybe that's what happened to you. Sorry this was such a long video.